Hello, everyone. I am Tatiana Risha, a third-year PhD student at Terrasol and École des Ponts Paris Tech. Terrasol is a renowned leader in geotechnical consulting in France and abroad. It is integrated in the CETEC group. My supervisors are Jean-Michel Pereira and Lina Goyakan from Navier Laboratories and Gilles Chaperon from Terrasol. Today, I will present to you a part of my thesis, which is the evaluation of settlement data collected during TBM excavation of two metro lines of the Grand Paris Express. The Grand Paris Express is the largest transport project in Europe, with 200 kilometers of new railway lines that are fully automated. It has to be noted that all of this metro system is excavated in very dense urbanized area. Therefore, it is very important to have a proper estimation of ground movements to avoid risks. In my thesis, thanks to CETEC, I have access to all kinds of information on parts of line 14 South and 15 Southwest. Altogether, they form about 13 kilometers of new, very well instrumented areas. The tunnel excavation can cause damage on the surface due to ground movements named settlement. To avoid that risk, we must be able to predict and quantify the settlements. So what does it look like? In theory, the settlement can be divided into two parts, the longitudinal settlement and the transversal settlement. The longitudinal settlement takes the shape of a cumulative probability curve, and the transverse settlement takes the shape of a Gaussian curve. These two can be calibrated by two parameters, the maximum settlement and a geometrical parameter noted I. To be able to predict the settlement, we must have access to the data that affect the ground movements. First, the TBM, or tunnel boring machine, is the machine used to excavate the ground. It has many parameters, and here I only noted some of them, which are the face pressure, the grouting pressure, the penetration rate, and all of them have a strong effect on the settlement. Soil parameters are the stratigraphy and all its mechanical parameters. It is very important to have these data to be able to tell what is the value of the settlement. Finally, the ground movements. We have many monitors placed on the surface and on buildings near the site of excavation. They measure the value of the settlement every 30 minutes, and we collect all this data in our database. Having all this quantity of data can be overwhelming. We are talking about more than 70 million observations. To make benefit from it, a long data processing is needed to transform the raw data into useful information. The data processing can be resumed into three big categories: the extraction of data, the cleaning, and the creation of a database. First, the extraction. The data was present on different platforms under different types like images or tables. The access was not always easy since we needed a massive extraction of all the information. We did some web scraping and used OCR functions to extract all the necessary information. The cleaning. It seems that the construction sites have the dirtiest types of data. It contains a lot of missing data, duplicates, outliers, and noise. So we used many methods to clean the data and some curved smoothing methods that we're going to see later on together, like the running median, to eliminate the noise and the outliers. And finally, the database. It is very important to create a database because it allows us to have all the data unified in one single platform. The integrity of data would be guaranteed because we have a relational database that we're going to see the architecture just next. The extraction of the data is very fast and very easily accessible by multiple users that we choose, and therefore the database and the data inside is very safe. This is what the entity relationship diagram of my database looks like. We can see in red right here, These are the tables that contain all the data related to the monitors or the sensors and their measured value, function of the date, and the distance to the face of the tunnel. In blue, we have the table about the tunnel boring machine parameters, so all the excavation parameters, and all the green tables contain the soil parameters and their mechanical parameters. You can tell that the three of them, or all the tables actually, are correlated or related to a table that I named ring. I could have also named it position because it contains all the information about the position or the spatial information, like the coordinates or the coordinates of the level of the tunnel, the base and the roof. We can note that this database is a relational one. I coded it in PostgreSQL. It was stocked on a cloud storage. So, before working on any type of model, one must choose which parameters to include in the study. Therefore, the feature engineering step is very important to reduce the number of parameters, which will give us a much more efficient model. Heat maps are the typical type of graphs that show us the different correlations amongst the parameters. Here I used a heat map to double check our choice of soil parameters. Indeed, if we take a look at one of the parameters, we see that it nearly has a correlation coefficient of 1 with many other parameters. So we understand that they are strongly correlated. If we look at these parameters that are correlated with each other, we can notice that they all have the same correlations with other parameters too. We should look horizontally to conclude that. So it would be inadequate to take them all together. Therefore, I chose these parameters based on the geotechnical knowledge, and it was confirmed based on the heat maps. It was validated based on the heat map. Another problem is to choose how to represent a stratigraphy with all its soil types and mechanical parameters amongst the input parameters of the model. I found an interesting method in an article written by Shen et al. In 2019, in which they introduce a novel approach that combines the soil mechanical properties, the thickness, written here with E, and the location of soil layers, uh, noted here with H. And there you go. We have all these parameters related, and we transform them into one single parameter. So for example, if we take the cohesion, instead of having here, instead of having 5 cohesions, we would have only one calculated with taking into consideration the thickness and the position of the soil layer, because you should know that uh, more the soil is thick, more it can contribute to the settlement, and the closer it is to the tunnel, the more it has an effect on the settlement. So these values, now we're going to have, instead of 5 parameter for each stratigraphy, we're going to have one parameter for one stratigraphy that would be introduced in our machine learning model as an input. Now, the purpose of our study is to predict the maximum settlement observed. Therefore, we needed to find a way to automate its calculation on the measured values by the monitors. Hence, the smoothing methods that are applied, like the running median method. On the left, we have the raw curve measured by the monitor. The running median is a very simple method where we calculate the median value for each interval, and then we move on to the next one. So there you go, you're going to have the median for each interval. And on the right is an example of what we would get after the calculation of the running median. We can see how smooth the curve is. And Once we have this curve, we would be able to calibrate the longitudinal settlement equation on it. So we would easily find the maximum settlement and the geometrical parameter I. And therefore, now we have automated the method to find the maximum settlement. Now comes the fun part with building the machine learning model. And up until now, we only tried the artificial neural network model because it is the one used most in the literature. The first challenge is to find the optimal architecture for our type of exercise. Because as you know, the artificial neural network have many parameters, from the number of hidden layers to the number of the neural in each hidden layer, to the learning rate, to the activation function and the batch size, the epoch size. So I can go on. I think there are some more. So it is not simple to know what would be the optimal architecture in our type of exercise. Therefore, we did a small exercise that honestly takes lots of time. It took like more than 12 hours running in the background, but it did success in the end. We did get the optimal architecture that I will show you just next. So how did we do it? We took only 4 kilometers of line. We took the data found on it, which leaves us with about 790 observations. We did the cross validation with a fold equals 5. And then we applied the grid search function on Python that does an exhaustive search for the optimal architecture. And that's why it takes so much time, because it is an exhaustive search. It tries all the parameters and the value of these parameters that we give it. And there you go. This is the optimal architecture that we found. We can see that the network isn't deep at all. It is only formed with 3 hidden layers. It was enough to deal with our problem. And we can also check the number of hidden neurons and the best activation function that was found. So there you go. The number of neurons are right here. We passed from 14 input parameters. Uh, then the neural network grew to 256 neural neurons, and it reduced to 64, sorry, and 32 to finally come with the output of one value, which is the maximum settlement, obviously. And once we know what to expect as an optimal architecture, we can now do a real application. We took the same data set, but this time we split it into 3 parts. We took 70% of the data as training set, 20% as validation, and 10% as test. The input variables are divided into 3 categories. The tunnel boring machine parameters, which are the velocity, the torque of the cutting wheel, the thrust of the shield, the pressure grout, volume grout, and phase pressure. The geometry category contains the distance to tunnel axis and the cover depth of the soil above the tunnel. And finally, the geological parameters that we chose are unit weight, parameters of the pressure meter test like the EM and alpha, the cohesion and friction angle, and finally the coefficient of earth pressure at rest. We did the 3 types of normalization based on the distribution of each variable. So for example, a distribution that looked like a normal distribution, we used the z-score method, and on others, we used the min-max normalization. And for the geometrical variables inputs, we found that it would be very logical to divide the value by the diameter, which in our case was equal to 10. So at the end, we have all values that vary between -1 and 5, if I am not mistaken, since the cover depth, maximal cover depth was found to be 60 meters, and the distance to tunnel axis about 50 meters. So yeah, the maximum value would be 6. And for the output value, we chose the log of the maximum settlement because we found that it highlights the correlations with all the input variables. And here are the results of our model. We plot the predicted values versus the real measured values, and then we check the R2 score. We can see that the R2 isn't bad at all, with values of zero point 0.7 and zero point 0.9 for the test set. Some would find it weird that the test set have a stronger R2, which is better actually. The bigger the R2 is, the better the correlation, the better the predicted values are. And we can explain the fact that R2 test is stronger or bigger than the R2 validation based on a statistical fluke when we split the data at the beginning. So there you go. In conclusion, the data processing is truly time consuming and it cannot be ignored. It is a necessary step before we do any type of modeling. Statistical analysis can be very informative on our data. It helps us choose the right parameters. Artificial neural network are the most used model in the literature, and therefore we decided to try it as a first example. But yeah, we saw that it's not a bad model, but we can definitely find others that are more adapted to our use case. And that would be our next step in my thesis. And it is to test all these other models like the XGBoost, the SVR or support vector regression, the genetic algorithms, etc. There are many that can be found and that have already been tested and that we would like to test on our set of data. So thank you very much for your attention. And please do not hesitate to contact me by mail at any time if you have any questions or would like to discuss further. And thank you.